Okay, we're in section 86. As always, there'll be contents to look over, examples to do, and then exercises. That's really going to take a lot of time to get through. Or usually it does for most students, especially if we take it seriously. My name is Ron Bannon. This is a draft version, and by adaptation, of Webster Wells Advanced Course in Algebra, which dates back to 1904. This document is being prepared for the Prison Mathematics Project participants only. However, at some point in the future, it will be published. If you're interested, if you're a teacher or student interested, and you want a copy of it at some point, you're going to have to email me. My name is Bannon, and my email address also is Bannon. That's B as in boy, the @ symbol, NNON.US. All right? So what I'm going to do is I'm going to briefly look through the content. And this content's about expanding a root of 1 minus x, and where they do the equate coefficients, and they go through that work. There's certainly other ways to do it. What I want to claim over here when you do it, that I graph two things for you. And I want to point out what I'm graphing over here. I'm graphing both this and a 10th degree series. So what do you mean 10th degree series? This is the series over here. So 10th degree, I'm going to just trace it out. I graph this thing over here, all right? Now, someone says it's really tough to graph. You're right, it is tough to graph, not for a machine, though, all right? Now, the claim over here, when you do it, though, I hope you realize that, one's in magenta, the other one's in black. The fit is impeccably good near 0. And then when you kind of band away from it, it looks like it's fitting between 1, and I'm going to say -1. The fit looks good there, all right? So I'm going to say between -1 and 1, it looks like the fit's pretty good, all right? Now, certainly, I want to point out in the text over here, they talk about that this is only going to work is if the x is between -1 and 1. Let me go back in the notes. This is clearly stated over here. So don't think the series is always true. It's just true for select values of x, and those x's have to occur between -1 and 1. So let me go to the actual example they want you to do. And certainly the way I write it up, the way Wells writes it up, is going to look different. All right, I just want to walk through it. As I walk through, I want to point out, if I were looking at this over here and someone could, assume there's a series expansion for it, what I mean by that is, if you look at this over here and I say, assume this is true for some value of x, how could you do that? You could equate coefficients, and the way to do that is, I would say, square both sides, because right now the left side's not polynomial. So once you do that, you get this expression over here. There is a problem, though. And someone says, what's the problem? It's squaring that infinite series, all right? So that can be tough, all right? Now, when I say it can be tough, I would recommend that you make some attempt to do exactly that, which is going to be a plus bx plus cx squared plus dx cubed, yada, yada, yada. And when you multiply it by itself, let me write this down for you. And again, this is a multiplication. I'll put a little star there indicating that. You could imagine how tough a cube might be. But this one over here, you're kind of looking at it. But, if you get again, equating, you're looking at this over here, there would be a constant term. And where would that come from? There's only one possibility for that. The 1 has got to come from a squared, all right? Now, I hope you realize that if x were 0, right, I want to go over here, because I really want to say, in this case over here, a could be plus or minus 1. Whoops. Let me get my eraser out. It doesn't look right. A could be plus or minus 1, right? But I hope when you're looking at this thing, A can't be plus or minus 1. Now, why is that? If you chose x to be 0, what would you get? You would get 1 equals A. All right? So there's no way it could be plus or minus 1. But again, it's equating coefficients. I also want to point out there's another good way to find out what the x is in the problem. I'm sorry, the a in the problem. Just let x to be 0. You get a as 1. Right? That's written over here. Now, again, I don't want to go through each one, but you should go through each one, all right? Let me start to erase this business over here. I'll erase this. I'll erase this. And I'm going to do another one, all right? Now, the other one I'm going to do is I'm going to do the linear term. And what's the linear term going to be? It has to be minus x. Again, it's right over here. And how could I generate that? Well, the only way I could get that is by bx. And the other one would be, let's see, another one would be abx, I'm sorry. A is 1, but anyway, abx. Like when I'm doing that, this times that, this times that. So when we get that, we have a linear factor of x. What does that mean? Minus 1 equals 2ab. And, what's a? We've already determined a was 1, right? So you get 2b. So what's b going to be? B would be minus 1/2. So forth and so on. And again, it gets tough, all right? It gets really tough. Now, what I mean by that is, kind of looking at it, if you thought about the left side, there are no squares. So you'd say there's 0x squareds. But now you got to equate the coefficients to get the squares. So I'm going to say acx squared. And then I get acx squared. Now let's see how we get the, I did that, right? AC, yeah, I did it. Let's do the bx times bx, which would be squared x squared. All right, so what does it say? 0 equals 2ac. I'm seeing that right here. I'm just equating the x's, x squareds, plus b squared. Now, again, you have to work your way backwards here. I'm trying to find out what c is. 2, a is 1. I do not know what c is. And what was b? B was minus 1/2, right? So you get 1/4. Again, 0, 2c, plus 1/4. Multiply both sides by 4. And I think it's pretty easy to determine what this is now. C is minus 1/8. And again, so forth and so on. But again, it gets tedious. There's no doubt about it. So let me erase that. Not a bad way to do something. Right, we'll go through examples. Or I should say we'll go through one example and you'll work a bunch of other examples. So I'm going to say get the coefficients, and hopefully as you do that, you start to realize you get a really simple expansion over here. All right? Now, by the way, I'm not going to say it's predictable, but I'm going to say you get an easy expansion, at least to the 4th degree. You got an easy expansion. We also want to claim this is a binomial expansion, where k could be any real number. And it looks like this over here. I think this is a little bit easier for most people to use, by the way, but you decide, right? You decide what to use. Now, I'm going to point out, if I were to expand, again, you do this using this over here. We did this one, and this one. You try this one, and you try this one over here. I'm just going to write down the binomial expansion for this. And how could you do that? It doesn't even look the same. You're right, it doesn't. Let me write this down for you. So the root of 1 minus x would look like this over here. The k would be 1/2, and you would get 1 plus minus x. Well, let me write this down for you. What do you get? And we'll get the same answer, by the way. 1 plus, what's the k? K is 1/2. What's the variable in this part? I'll outline that for you. Is this thing right over here. It's actually minus x. So I'll write that down for you. We'll simplify it later. Plus k, which is 1/2. And again, for this is easier for me to write down. Your mileage may vary. And 1/2 minus 1 is minus 1/2. I'll simplify it later. 2 factorial is 2. And then you're going to get minus x quantity squared. Let's put the next one down. What's that going to be? 1/2. And 1/2 minus 1 is minus 1/2. Now, I'm not saying you can't make mistakes, but I think it's harder to make a mistake if you have a simple pattern. And what do you get? 1/2 minus 2 is minus 3/2. And what do you get in bottom? 3 factorial, which is 6. And then what do you get? You get minus x cubed. Right, I'm going to put a next term down. Boy, I'm kind of running out of room, aren't I? Let's write this down. So what would it be? 1/2 minus 1/2 minus 3/2. Next one would be 1/2 minus 3. That would be, let me write that down for you, 1/2 minus 3. Well, that would be 1/2. 1 minus 6 minus 5/2. They have a very nice pattern, by the way. And what do you get now? 4 factorial, right? What's that? 24. And then you get minus x to the 4th power. Let me write this over here. You know what? That doesn't look right. I'm going to clean that up a little tiny bit. But before I do that, I want to start writing the terms down for you. And I want to tell you what I'm going to clean up. This thing looks terrible to me. I'm going to clean that up later. Let me start writing this down now. You can get 1 minus x over 2. I'm just clipping these off one at a time. What's the next one going to be? Oh, boy, that's going to be minus, isn't it? And let's see, you get 1/4, 1/8. Okay, so it's going to be minus 1/8 x squared. I got that done. We'll look at our key later. This one's more complicated. What do you get there? I can't read my own writing, can I? So it's minus 1. Let's see. It's still going to be negative. All right, still going to be negative. Let me get my eraser out. This doesn't look good either. And again, we're doing this term over here. I'll clean up the other one a little bit later. Let's see. I'll get my eraser, get my chicken scratch gone here. I get 6 on the bottom. 2 times 2, 4, 8. Another 8. On top, I get what? I've already resolved the sign of it. It's negative. And you got an x cubed. That's true. And what do you get there? It looks like you get, let's put the number down. This is the tough part, right? So it looks like you get 3, right? What's that going to give you? Oh, 16. Put it over here. Yeah, 16. All right? Because 3 goes into 6 2 times 16. Now I got to clean something up over here, okay? Let me leave this over here. And that last term I'm going to clean up a little bit for you. It just doesn't look right to me. I'm going to write that down now. Plus, let's see, 1/2 minus 1/2 minus 3/2. And remember what I said before. It's going to be, 1/2 minus 3. That's minus 5/2, right? You should see a very nice pattern to this. And then minus x to the 4th power. And what goes on bottom? Let's see. It's going to be 24 now, 4 factorial. A lot of computation. But let's look at the sign of it. And it's going to be negative. Negative again. And just looking at the sign, you get minus, 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 which is a negative number. And minus x to the 4th power is just x to the 4th power. So I'm going to put x to the 4th power down. I'm kind of wondering what the fraction's going to be. I'll write this down. It's 24 in the bottom. I got a bunch of 2's. 2 times 2 is 4, times 2 is 8, times 2 is 16. And what do you get on top? Well, let's take a look at that. I already got the sign resolved, by the way. 15. Well, I notice that 3 divides top and bottom. So I'm going to say 3 goes into 15 5 times, and it goes into 24 8 times. And then 8 times 16 is 80 and 48. That's 128. And now I'm seeing a number on the top, which is number 5. So I'm going to say over here, we're getting the same result. But again, someone said, that's just too much work. I'd rather just, take the other formula. That's up to you. You decide what you like doing. I like this thing over here, but you may like this expansion over here. When I say that expansion, figure out the coefficients and then getting through that. All right, you can do that, not a problem. All right, I kind of like this over here. What's nice about this? It works for any k. All right, any k at all. All right, let me go to the next thing up, and I'll talk through it. There's exercise here. What's exercise? You're going to be given this over here. As you're doing these problems over here, again, I want to recommend that you use that thing I just said, binomial expansion. Write it as a binomial. 1, and let me point out what I mean by that. We're doing this thing over here. So I got to write this down as 1 plus minus 4x raised to what power? 1/2 power. All right, and then you follow this thing over here. Again, I believe it's the easiest. Your mileage may vary. All right, but anyway, let me point out this to you over here. What I do is I go through the work, and I put an answer down here for you. In addition to writing an answer down for you, what I also do is I graph a picture of this thing here, and I graph a picture of the expansion to the 10th degree. Let me put what I mean by that. The 10th degree expansion. Now, someone says, how'd you do the 10th degree expansion? I'll be honest with you. I cheat a little bit. I actually use a computer because I don't want to compute those numbers. They're really they get bad quick. There's no doubt about it. In the beginning, they're okay. This converges between minus 1/4 and 1/4. And I put a picture down for you. Someone says, why do you put a picture down? We want you to look at it. We want you to look at those pictures. And certainly I want to point out the number minus 1 over here, 1 there. 1 would be over there. It looks like the fit is only in this region over here. That's where the fit is. And where would that be? Well, we're going to say between minus 1/4 and 1/4 only, not including those points, by the way. So I think I do that for the problems. This one over here, again, I use that binomial expansion. I find it easier to do, but again, your mileage may vary. This one over here, you may see that it's going to be tricky, but I still would use a binomial expansion on that one. Now, someone says, how would you do that? Well, one way you could do it is just simply write down what a binomial expansion might look like over there. Let me see if I can do that. And I realize I did different work over here. Let me get my eraser out. I'm going to look at that radicand first. And what do you see in the radicand? 1 plus 2x minus x squared. And again, I'm going to talk a little different way of doing it. And let me write this down over here. See, that doesn't look like it's going to work nicely, does it? 1, and then you get what over here? X and x. Now, you're not going to get it. So minus plus, that wouldn't give you that. If you did plus plus, you wouldn't get it. Minus minus wouldn't get it. You get the idea. It's just not going to work, all right? So what I'm going to tell you is I'm going to try another technique, all right? And again, you play around. I think playing around with things is a good idea. And I'm going to try to complete the square on this. And I'm going to write a little differently. I'm going to put down 1 minus, and I'm going to write this down now as x squared minus 2x. Hope I didn't go too fast with that. Again, we're taking this and just rewriting that. And then, of course, if I write that down, what do you get? I got to complete the square on it. So x squared, half of minus 2, right, would be minus 1. You square that, you get plus 1. I'll write that down for you. Now, remember, you're subtracting 1, so you're adding 1. So this would be 2. All right, I want to show you this is a true statement. This is 2 minus, I'm going to erase it later, minus x squared plus 2x minus 1, which is what? It's going to be 1 plus 2x minus x squared. Look at my eraser. I'm convinced it's true. And I'll tell you why I did this. What do you get over here? Again, this might seem like too much work. You don't do that work. Then you do what you find convenient. What do you get over here? 1 minus. And what do you get there? You get what? You get x minus 1 quantity squared, all right? I know there's issues with this. Somebody's looking at it and said, where's this going to stop? It's going to stop when I see it, all right? So one thing else I could do to that, I could factor out a 2. Let me put that down for you. And then you would get 1 minus, let's write this down now. That will be x minus 1 over the root of 2 squared. All right, let me see if I did okay there. Yeah, I think so. Looks pretty good. All right, and then it's really the square root of that. I'm going to start to erase things. You know, chicken scratch over here. We can get rid of that now. And again, my claim is this is the same thing as what they have written over there. Same exact thing. Now, someone says, what do you mean the same exact thing? If you were to multiply it out, what would you get? 2. I'm going to erase this later, by the way. 1 minus, well, let's square it out. What do you get? X squared minus 2x plus 1 over 2. And if you multiply this out, you get 2 minus x squared plus 2x minus 1, which is going to be 1 plus 2x minus x squared, which is exactly what they said it is. All right? Let me get my eraser out, and I'm going to point out as I'm doing this over here, don't be intimidated. You might say, I don't want to do that work. We're not telling you how to do it work, nor would I suggest to you this is a way to go. I would not suggest that. I'm just suggesting you might see these things as being a little bit different. So I'm going to claim that this guy over here is the same thing as the root of 2, 1 minus this thing here, which looks crazy to me, but I'll write it down for you. It's going to be x minus 1 over root 2 squared. All right, get my eraser out. What do I do now? I guess I could write this down for you. Root 2. And then I can write this over here. This would be the root of 1 minus, and this would be what? X minus 1 root 2 squared. All right? Now again, there's tricks you could do with this one as well. But I want to point out, let me go back up here, that this is sort of in this form over here. There is a slight difference. Let me go back over that with you. So I'm going to rewrite this one over here. Root 2, whoops. Root 2, I'm writing this as a power now. 1 plus, I'm going to put this in a square bracket, minus, and yeah, if I a lot of students, it just overwhelms them. They don't want to do that. And what power is that? 1/2 power. And you can just provide an expansion on that if you want, all right? Now, again, a lot of people say, no, it's just too much work. Why would I do that? You're right, it might be too much work. So what you could do is equate coefficients. Now, by the way, if you're going to equate coefficients, it says at least 5 terms. So what do? Write it down like this, square both sides. The problem, again, is doing this and equating coefficients. We put the work down for you, though. So you want to make sure when you're doing this, you're getting these matches over here. If for some reason you're not getting those matches, maybe I made an error. It's unlikely, but maybe I made an error. So I'm also going to say that, I don't know why I wrote that down. Let me just make sure. I think I need to correct this. This needs to be corrected. I'm not sure why I wrote that down. I have to look at this again, look at again. And yes, I will correct it if it needs correcting. But that clearly not the problem, all right? Clearly not the problem. So let's see what we got over here. And this one over here, same thing, expansion. I'm going to say the expansion looks good, but there's no work. There's no work here. Now, by when I say the expansion looks good, you should try to get that expansion. One of two ways, equate coefficients or use binomial theorem. This one over here, I would definitely use the binomial theorem. It's written that way, where the k is 1/3. That's also written for you over here, all right? This one over here, equate coefficients. That's written down for you, and the expansion is written down for you as well. All right, let's get to the SAGE part. I think it's important for you to look at that. However, don't do the problems using SAGE. What's SAGE? Computer Algebra System, CAS for short. It's open source, which means it's free to obtain. They're not asking for money for it. However, you can donate to the organization if you like. What are you going to do? Go to that website. You either download it or use the direct web-based application. Again, I want to pick up this thing about Taylor. That's a command that's used in SAGE that would allow you to expand these things incredibly quickly. Right? I mean, really quickly. It's like shocking how long it takes us to do by hand, how quick it does it. All right, how quick it does it. All right? So let me repeat this. We'd like you to work the problems. As you work the problems, if you have any questions, please bring it to my attention by emailing me. What's my email address? The B as in boy, the @ symbol, NNON.US. All right, that's my email. What could you tell me? Well, if you're in this section over here, and if you're doing problem number 1, but don't give me the page number, by the way. Just simply say, oh, I'm in section 86.3. Someone says, why don't you use the page number? Page numbers change. The sections aren't going to change, though. These sections are cut in stone. They're really reflecting the assignments that Wells developed. This is the 86th assignment. So the assignment number's not going to change, but the page number will change. But if you're in 86.3 and you say problem number 1, and I think there's an error, let me know what you think the error is. I will carefully look at what you write me, and I will carefully look at what I've written down. And if there's a correction due, I'll make the correction, and I'll give you credit. All right, I'll give you credit. Your name will appear in the notes, unless, of course, you don't want your name appearing in the notes. All right, I hope this has been helpful, and I really do appreciate the attention that you've given me. Thank you.